Hello, welcome back to 271 Math. I'm your host Jamie, and today's topic is summation notation, also known as sigma notation. Summation notation is a clear and concise way to write a long sum of numbers, and it is denoted by the Greek letter sigma. So let me write that out. So up top we have n, below we have I equals 1, and to the right of it we have any expression. Let's just say this is I. So I is our index variable. It represents the current term being added. I equals 1 beneath the sigma sign represents the starting value of I. Typically, you would see I equals 1, but it can be any number. And the n above the sigma sign represents the ending value of I, also known as how many terms we add. So, and this expression, it tells us what to do with each term, in this case, simply adding I. I think it'll be easier to see if we perform it. So, let me write an example. So, say you have a series of numbers that you want to add up. For example, 1 plus 2 plus 3 plus 4 plus 5. Writing this out explicitly is manageable for small series like this. But what if we wanted to add up the first 100 numbers, like 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so on, so on, so on, until 100? That would be tedious and it would be prone to errors. This is where using summation notation would actually come in handy. So, how do we represent that? We have the sigma symbol from before, 100, which is our ending term, and how many times we're adding up. We have I equals 1, which is the starting value, and then over here we just simply have I. So this sigma symbol indicates that we're adding up a sum of terms. With sigma notation, it is vital to substitute the next occurring whole number up until n. So in this case, n equals 100. So this would actually be 1 plus 2, which is the next whole number, then 3, then 4, which are the next whole numbers, and then so on, so on, so on, until we are at 100. So sigma notation is handy for arithmetic sequences, but that's a topic for a later video. And it is also handy to represent long, tedious sums. Let's go to some examples. We have the sigma symbol, 5. Our expression is going to be 3i. And for our index variable, we have I equals 1. So we start out substituting I. We have 3, and I in this case is equal to 1, plus 3, the next occurring value, which is 2, 3, 3, 3, 4, and 3, 5. So we have 3 plus 6 plus 9 plus 12 plus 15, which is equals to 45. And that's our answer for our first example. Let's go on to example number 2. So for this one, the index variable could be any letter. It doesn't always have to be I, so let's just say this is K. Let's write 6 on top. And for the expression, let's write this 1 plus K squared. So our starting value is 1, so we substitute 1 first, so we have 1 squared, plus, actually let's write this in parentheses because it'll be easier to differentiate, plus 1 plus 2 squared, which is the next whole number, plus 1 plus 3 squared, plus 1 plus 4 squared, plus 1 plus 5 squared, plus 1 plus 6 squared. So if you take all these values, we would get an eventual answer of 90. But you see how long that took me to write out? If we simply roll this into a calculator, this summation notation, it would give us 90 automatically in a much shorter time. So that proves the point that summation notation is easier for writing long and tedious sums. This would have been even more convenient for an even longer tedious sum, like if we had 100 up here, that would be pretty inconvenient. So for example 3, we could sometimes see that for our expression, we don't have any variable, but rather a constant, let's say 10. This is okay and common as well. Simply, we would go about like we would with any regular expressions, starting at the index variable and summing up until 10. So let's just say that we have 4k equals 1 and 10. So for this, we would just start out at k equals 1, our first start. This would be k equals 2. This could be 3k equals 3, and this would be k equals 4. So this is just equals to 40. That's our answer for example number 3. And finally, for our last example, we could also have infinity as our end value. This sum would be only possible if the expression is a fraction where the value of the denominator is greater than that of the numerator. So something like this. Infinity, let's say I equals 1. And then for our expression, we have 3 over 10. Oh, oops. 10i. So let's write that out. We have 3 over 10 times 1 plus 3 over 10 times 2 plus 3 over 10 times 3, and so on, so on, so on, until we have 3 over 10 times infinity. So our answer with this, for this, would just be 0.33 repeating. This is also something common that you would see. And if the numerator, this value, is greater than the denominator and n is equal to infinity, the answer will also be infinity, or it would be incalculable because you have so many terms you need to add up. So, in summary, you could denote tedious sums using sigma notation. Thank you for watching.